Let's talk about planetary positions with respect to the sun. We're going to be dealing with a couple topics here, and that is opposition, inferior and superior conjunction, quadrature, and greatest elongation. So why don't we start with opposition? Now, you've probably read about this in a book, but just give you a little visual reminder here of what we're talking about, and then we'll apply it to a couple different situations. So let's first start off with what we think opposition means. Opposition is when turns out that the Earth is located between the Sun and another planet. Why don't we put Mars out here as our planet? So you see that if you draw a line between the Sun to the Earth and then out to Mars, you have 180 degrees here. That's the farthest these two objects can get apart in the sky. So what I want to draw next is what we call a horizon sketch. And we always do it from east to south to west, ESW, if you can remember that. Because if you're standing out on the out, maybe looking towards the south here, this is out on a field, and you're looking towards the south. When you point your arm to the left, you're going to be pointing towards the east. When you point your arm to the right, you'll be pointing to the west. So in a sense, you can see here how we have this progression from E to S to W. And even though this appears as a flat line up here, in terms of a horizon, we know that if we took that and moved it down here and stretched it around to make it more three-dimensional, it would be ESW. So what we're going to do is convert this picture of the solar system here, what we might call an orrery, that is kind of a picture of the planetary orbits around the sun. We're going to convert it into this, which is a horizon sketch. So let me clean up things here for a second, and then we'll go back and finish our horizon sketch. So let's draw a horizon sketch then for this particular situation where we have opposition. Notice again, we're standing on the Earth. When we look in one direction, we see Mars. When we look in another direction, we see the sun. So I can choose perhaps any time of the day or night. Maybe something that's convenient would be 6 a.m. when the sun is rising in the east. Where would we look for Mars in that case? Well, it should be 180 degrees apart, so Mars is going to be somewhere over here in the west. Okay, and let me go ahead and draw this picture again here. You're standing out in the field, and you're looking towards the south. Over here is the east, over here is the west. So when I look towards the east, the sun, in a sense, is coming up, but Mars is now setting in the west. All right, and you can see that again. When I point to these guys, they're 180 degrees apart. One arm would point towards the sun, the other arm would point towards Mars, and your arms would be held up at 180 degrees apart. So now we have translated our orrery into a nice little horizon sketch, and this is the situation for opposition. Now let's take a look at conjunction. There's two kinds of conjunction. We'll study both of them. The first one we'll see is inferior conjunction. Inferior conjunction occurs when you have the Earth out here, the Sun over here, and then you have a planet that is between the Sun and the Earth. So let's go ahead and maybe call this one Venus. Now, it's a little bit hard to say exactly when conjunction occurs. If you think about it, it could be somewhere in here. What I'm drawing is maybe from there to there. When we look at Venus from standing on the Earth here, look at Venus, it's still pretty close to the Sun. It doesn't have to be exactly between us and the Sun for it to be in conjunction, and inferior conjunction in this case. So like for instance, maybe Venus would be right here, or maybe Venus would be right there. And both these would be considered inferior conjunction. Okay, so let's go ahead and just put Venus right here between us and the Sun, with the recognition that there's a little bit of flexibility in exactly where Venus might be to make it inferior conjunction. All right, so they're together in the sky. Now, how would that appear for us if we went outside and looked on a horizon? Do you remember the sequence of letters? It's E, S, W. And since we took 6 a.m. up here, let's go ahead and take 6 a.m. down here as well. The sun then would be rising in the east. And then as we look out towards the sun, we'd also see Venus very nearby. Now, especially if Venus were up here or down here, we're just going to put a little V here for Venus, and you see that they're together in the sky in conjunction. You might remember when we were kids, the Saturday morning cartoons, little ditty that went conjunction, junction, what's your function? Conjunction means putting two things together. And so here we have the Sun and Venus together. Now there's another type of conjunction besides inferior, and that would be superior. So I'll do that in red here. Superior conjunction. Very similar, except now the Earth is over here, but the planet happens to be on the other side. So again, you see how from the Earth's perspective, there's the Sun, but if you look beyond it, Venus might be up here or it might be down there, and it's still very close to the Sun. Again, in this case, we'd call it superior conjunction. So how might it appear over here? Let me back that up here. It looks like I'm doing all my horizon sketches in blue, so let me go ahead and do that. How might that appear? E, S, W, and there is the Sun rising in the east. Again, if it's 6 a.m., we'll just write that out over here. And then how would Venus appear? It's very close to the Sun, so it might be something like this. And we see that these two horizon sketches look almost identical. In fact, from these, if we went out and looked at the situation with inferior or superior conjunction with Venus, we'd not be able to tell them apart. From the naked eye perspective, Venus here and Venus down here would look exactly identical. What we'd have to do is look at them through a telescope and see how they're lit up. So I think you can see that, well, I won't explain it quite right here, but it turns out that I'll just tell you what the answer is. That right here, Venus is mostly lit up because the Sun is shining fully on it. Over here, Venus is more of a crescent shaped because this side of Venus is lit up and we're looking at the dark side of Venus. So in other words, if I could go ahead and show what this Venus would look like, it would probably be more like a crescent shape like this and pretty large, or it could be a crescent shape like that depending on which side of the Sun it's on. This is how it would appear in a telescope. We can't see this crescent shape with the naked eye. Or it might appear like this. But down here, where Venus is on the other side of the Sun, it's going to be smaller because it's further away from us. And instead of a, it's going to be slightly what we call gibbous shaped. It's going to look something like that in a telescope. Because the part that's lit up, let me go ahead and get rid of this and show you right here that if that's Venus, this part is lit up from the Sun. Okay, the Sun's shining light on Venus. That light shines back to us on the Earth. And from our perspective, looking at least through a telescope, Venus would be mostly lit up. But of course, it's small. But the point I'm trying to make is, if you forget the telescope and just go with our naked eye observations, that these two drawings here are entirely very similar. And so Venus appears the same to our naked eye, whether it's inferior or superior conjunction, and you're going to have to look through a telescope to see what the relative size of Venus is and the shape of Venus in terms of it being lit up before you can tell whether it's inferior or superior. But don't worry about the telescope stuff for now. Just worry about how it might appear on our horizon sketches to the naked eye. I'll clean up and then we'll go to the next one. For our next planetary position, we're going to be talking about something that's called quadrature. Quadrature means 4, and if you take 360 degrees and divide it into 4, you have 90 degrees. So this is a situation as well where you might have the Sun right here, and then the Earth right here, and then you might have a planet such as Mars above us. Mars continues in its orbit about the Sun. Should draw a larger orbit here. Okay, but at some point, Mars may form with the Sun a 90-degree angle right here. And that's what we call quadrature. Let me get rid of my little orbit here. A little bit hard to see. But I'll redraw that 90 degrees. So, oops, went a little too far. Let me get some of that stuff back. So there's Earth, there's Mars. And when we go like this, we have 90 degrees right there. Now notice the most important thing about this feature is that the Earth has to be at the corner, the 90-degree corner. It's not the Sun at the 90-degree corner, it's the Earth. Now, how would this appear in the night sky? E, S, W. again, we're going to go with the 6 a.m. where the sun's rising in the east. And it turns out then that Mars would be at a 90-degree angle. From here to here, you have a 90-degree angle. In other words, it might be a little bit hard to show with this particular sketch, but there would be the sun rising east, and then in my southern sky, Mars would be right here. If I point one arm towards Mars and the other arm towards the sun in the east, that forms a 90-degree angle. So let me clean up a little bit and we'll talk a little bit more about. One thing you might notice here about quadrature is that some planets cannot be in quadrature. For instance, if I take a look at a planet such as Venus, let's get Venus kind of a light orange here. Here comes Venus coming along. And you notice there's no way that Venus, in its orbit about the sun, can reach a position of quadrature with respect to the Earth. Venus is never going to be down here. It's never going to be up there. And so Venus and Mercury is another planet, can never be in quadrature. Okay, well, let's move on. I probably need to, it looks like I'm going to have to look at the greatest elongations, the next one that we want to talk about here, but I'm going to have to do it on a new screen. So hope you don't mind me doing that on a new screen here. Let's go ahead and talk about it. And let's say that we want to work with purple on this one. So this is called greatest elongation. Now what I'm going to do is draw the sun here. And then I want to draw a real nice little planetary orbit about it. And let's say that this is, this one here is the orbit of Venus. And then out here I want to put the Earth. And I'll give you a couple positions. You can write this down if you want to, or you can just watch it if you'd like. Let's say this is position A, this is position B, this is position C, and this is position D for Venus's orbit. Okay, so maybe at 4 different times in its orbit. And then I'm going to draw a couple straight lines here. First of all, between the Earth and the sun, and then to each of these positions as well. Now, you can see what I've done for D and C. If I had to measure this angle right here, oh, this angle here is probably about 10 degrees. This angle here is about 20 degrees. I might ask, if I look out in the night sky here, E, S, W, and you can really see like position D, looks like D got moved on me here. Let me see if I can get D back in its proper place. If I looked at position D, perhaps the sun would be rising in the east, and you look at position D, Venus would be almost in what? Right in here, Venus would be in inferior conjunction. So this is like Venus at D. And we might ask, how far apart are these guys in the sky? If I held my fist up, you can see that at this point, I'd hold only one fist, right? Considering the fact that a fist is about 10 degrees. Maybe at position C, if I change colors here and go to position C, C would be probably further out here, so this is Venus at C, and that might be like 2 fists. The point is that my question is this: at what position, A, B, C, or D, I think we already can throw out C and D, will Venus be the furthest away from the sun in the sky? The furthest angle it can be away from the sun in the sky is going to be A, B, or C. You should pause the video, and I'm going to go ahead and clean up here. You should pause the video and just look at this picture and answer. Is it A, B, or C? We know it's not D because C is already 20 degrees, and that's greater than D. Well, if you answered B, then you would be correct, because you can see that this green line I've drawn, especially in green here, the green line is at a greater angle. It looks like I need to turn off my straight line there. The green line is at a greater angle than the red line, or the purple line. This is around 40, 47 degrees, 46 degrees or so. But for the red or the purple line, A, position A, if you will. Here's position A. Look at that. That's less, isn't it? That might be 45, 44 degrees. But what I really want to point out here then is, let me go ahead to orange over here, that at position B, Venus is the furthest it can get away. Venus at B is the furthest it can get away. And it turns out it's around 47, 46 degrees or so away from the sun. That's what we call greatest elongation. It's the furthest that Venus can ever get away from our sun in our night sky or our early morning sky, whatever the case may be. So this position right here is called greatest elongation. Mars similarly also has a greatest elongation as well. Okay, but that makes a lot of sense for planets that are between us and the sun, namely Venus and Mercury. Because we know any planet that's outside of us, such as Mars or Jupiter, what's the furthest they can be away from the sun? Mars and Jupiter can be out here, right? Maybe this is Mars. How far is it away from the sun in this case? Well, here it's in opposition. What was that angle again? 180 degrees. So when we talk about greatest elongation, we're really only talking about these two planets right here, because Mars on out, those guys can be at 180 degrees. Okay, so there's greatest elongation. Now what I'm going to do is spend a little bit of time showing you how these manifest themselves. We're going to look down at an orrery of the solar system. Here we're using a program called Starry Night, and we're looking down onto the solar system. I know the words here are a little bit small, and I can only show you with my mouse what's happening, but there's the sun in the middle, and then we have Mercury over here to one side, and then we have Venus up here, and then we have the Earth over here, and to the outside, I'm not sure if you can see it or not, is Mars over here. Now what we're going to try to do is let time run forward. Up here we're having it run at 12 hours at a time. And let's go ahead then and take a look at our at what's going on with our planets. Looks like I lost the names of my planets, so let me pause it and fix it here for a second. Okay, so we got our planet names back. Now, I want you to find the Earth. You see where the Earth is, right? It's over here. You'll see the Earth, okay? Let's see. Why don't we go first for, why don't we just say, when is the next case? Let me run time on here a little bit and see what happens. All right, so the planets are going around the sun. And tell me when Venus next comes into inferior conjunction. Tell me when to stop the video. Venus, inferior conjunction. About right there. Do you see that there? Notice how the Earth, Venus, and their sun are lined up. That would be a position of inferior conjunction. Then as we run time forward a little bit, of course Venus is moving faster. It's on a smaller orbit than the Earth. Tell me when to stop the video for superior conjunction for Venus. When will Venus be in superior conjunction? So we let time run on. Time keeps going on. We're now many months into the future. And where's superior conjunction? I probably went just a little too far, didn't I? Maybe somewhere right in here. We see here's the Earth, there's the sun, and Venus is on the other side of the sun. That would be superior conjunction. Now, how about opposition? Can we have a case of opposition for Mars? Think about that. Look what's happening here. We almost are set up. We're now in the year 2010, by the way, a little off in the future. Look what happens here as I run time forward. Maybe I'll just do it a little bit of a time here. Let's go ahead and hit play. And about right there, maybe just a little bit farther back, somewhere in here, we see that the Earth is in between Mars and the Sun. That would be a good case of opposition. Pretty nice, eh? Now we might ask, the next thing for us to do is look at quadrature. Okay, let's let time run on a little bit further here. And when is the Earth and I should say the Sun and the Mars, when are they going to be in quadrature with each other? Well, you can see just about now is a good example of quadrature. Let me just go forward a little bit here. And that's not too bad right there, because if you go from the Sun out to the Earth and then over to Mars here, this forms a right angle. It might not be perfect. I might need to adjust maybe a couple more days, but for the most part, this forms a 90-degree angle with our orrery. So if we looked out in our night sky, we would see a situation like down here where Mars and the Sun are in quadrature. Okay, hopefully this makes sense. You can rewind that video if you'd like. I'm not going to show greatest elongation necessarily. I'm not going to show greatest elongation with starry night, but you can imagine if the Earth is located right here, greatest elongation for Venus would probably be somewhere about right in here where you see my mouse moving around. Okay, that would be greatest elongation. Or on the other side, somewhere over here, you might also have greatest elongation as well. Here you have a chart that is not shown in your textbook, but I would encourage you to get out a blank piece of paper or find a place in the textbook by which you can write this down. So you should pause the video now and write down this table. It shows Mercury and Venus, Mars, Jupiter and Saturn, the Moon, and then along the top here are our various things like opposition, inferior conjunction, superior conjunction, quadrature, and greatest elongation. Pause the video now if you want to copy down this table. Okay, so the question we want to ask ourselves is, how would we fill out this table? For instance, in this first box right here, we're going to ask, can Mercury and Venus ever be in opposition? So we come back here and we ask, can Mercury and Venus ever be out here in this place on the other side of the Earth from the Sun? Can Mercury and Venus ever be there? I think the answer is, as you can tell, the answer is a big capital NO, right? It's not possible. Can Mercury and Venus be in inferior conjunction? I won't flip back all the time here, but you'll see that, sure, we use Venus here as a good example of inferior and superior conjunction. So we're going to definitely say yes here and a big yes here as well. Can Mercury and Venus ever be in quadrature? We look back here. Can Mercury and Venus ever be up here? We already talked about that actually, and the answer is no. But can Mercury and Venus be in greatest elongation? The answer there is yes. E.g., we found out that for Venus, it was around 46, 47 degrees for Venus. So the answer is a definite yes. Let's then turn our attention to Mars, Jupiter, and Saturn. Can Mars, Jupiter, and Saturn be in opposition? Absolutely. That's the example that we used up here. In the case of Mars, it was in opposition to the Sun. So we'll say yes. How about inferior conjunction? Can Mars, Jupiter, and Saturn ever be here between the Earth and the Sun? Mars, Jupiter, and Saturn. Can it? I think you know the answer is no. All right. How about superior conjunction? Can Mars, Jupiter, and Saturn ever be out here, somewhere out here, on the other side of the Sun, in the orbit? Absolutely. Because if this is the Sun right here, and the Earth is down here, why can't these planets be out here on the other side? Mars, Jupiter, Saturn, right? So for sure, these guys can definitely be in superior conjunction. So the answer is yes. In quadrature, the answer is yes. We talked about that. Greatest elongation, it really doesn't make sense, so we'll say no, because as we said, these planets can be as 180 degrees away from the Sun. That's what opposition was all about, right? Okay, the next thing we're going to take a look at then is the Moon. To help us with the Moon, we're going to go back and look at Starry Night here and see what we can find. again, I'm looking down onto it's an orrery, I'm looking down onto the solar system. The sun I've moved down here, and the Earth is up here. What I'm going to do is try to zoom in to the Earth. Now remember, the sun is at the bottom of the screen. So when I zoom in to the Earth, hopefully I'll be able to see that little green circle, and that would be the moon. Let's go ahead and slow our time down here. I think 12 hours would be far too fast. Maybe we should just go to 3 hours. Let's see how this goes. Not too bad. We'll slow it down just a little bit further, maybe to 1 hour. And you can see, and I probably should turn the stars off because they're a little bit of a distraction in the background. So let's see if this works. Okay, the stars are gone. Now, do you remember where the sun was? The sun was down here at the bottom of the screen. Here's the Earth, and now we have what we call a first quarter moon right there. What position is that? That is called quadrature, right? That's quadrature. So we can have quadrature with the moon. Remember, the sun is down here at the bottom of the screen, and then there's the Earth forming the corner, the right angle. If we let time run on a little bit, what's the next situation? Right there. The moon is opposite the sun in our sky. That would be a full moon. And what's the position called? Opposition. Exactly. Let's run time on a little bit further here. You tell me when to stop next. Right there is the third quarter moon. And what position is that? Moon, Earth, Earth, Sun. That's another example of quadrature for a third quarter moon. Tell me when to stop. We'll stop right there, maybe just a little bit further, and we would have what's called inferior conjunction. The moon is between the Earth and the sun. Okay, so now we're going to go back and fill in our chart. So let's finish our chart here. We said that the moon is in opposition with the sun once a month, and that would be a full moon. Is the moon in inferior conjunction? Yes. Turns out that's called a new moon. And was the moon in quadrature? Yeah, it sure was. A first quarter and a third quarter moon were in quadrature. And greatest elongation doesn't really make sense, so we'll just put, yeah, it doesn't make sense because we know that a full moon is 180 degrees apart. So just like the other guys, for Mars, Jupiter, and Saturn, it really doesn't make sense to talk about the moon as in greatest elongation. Now, how about superior conjunction? When we ask this question, basically we ask, here's the Earth, can the moon ever be over here on the other side of the sun? I think you see the answer is a big resounding no. Okay? So this is a nice little chart. I would suggest that you know this chart well, but not because you've memorized it, but only because you know what it means for opposition, inferior, superior, quadrature, and greatest elongation. And the other thing too is not only to know what these planetary, or moon in this case, when we just talked about the moon, what these positions are with respect to the sun. The idea is that when we go out and we communicate with other astronomers, oftentimes when we go out, we actually use this terminology with them to describe the planetary positions. When we go out and we see Mars setting in the opposite direction of the sky than the sun, we use terms like opposition to describe it. So whenever you see things happening in the night sky that are in some of these positions, of course, they don't have to be in these positions. The moon is only in particular positions four times in a month, right? When it's a full, new, first or third quarter. The rest of the time, it's not in any particularly interesting position. So planets do not have to be in these positions, but sometimes they are, and when they are, we make special note of it. Okay, so that's it. I hope this has helped you in your understanding of planetary positions with respect to the sun.